All right, so let's start from where we had left off in the last lecture. If you recall, we were discussing that an amplifier. We were discussing voltage amplifiers, and we had said that a ideal voltage amplifier has a linear relationship between output voltage and the input voltage. Linear in the sense that the voltage gain that you see here, AV, is a constant. But in practice, amplifiers are not ideal. They have a variety of non-idealities, and some of them are listed here, that the gain that you find here depends on a number of other factors here. Okay? And what we are going to do is look at these factors one by one. And last lecture we had seen that gain, voltage gain of an amplifier is a function of frequency. And typically the gain falls at very high frequencies and gain falls at low frequencies as well. And there's a region which we call as the mid-frequency band, where the gain is relatively flat. And so the amplifier, besides the voltage gain here, which we call as the mid-band voltage gain, is characterized by a bandwidth specified by the lower cutoff frequency FL here and the upper cutoff frequency FH here. So those are two other important parameters of an amplifier, FL and FH. And we said that some of the amplifiers, because of the way they're designed, they do not have an FL. They can amplify right from DC onwards to some higher frequency here, and we call these as DC amplifiers. And DC amplifiers only in the sense that they can amplify from zero frequency onwards. Besides that, there are multiple ways in characterizing the frequency response. Sometimes you'll hear or you'll see a parameter called unity gain frequency. We just said that the amplifier gain falls at higher frequencies. And if you go to sufficiently high frequency, the gain will fall to a value of 1, which means 0 dB. And we call that as the unity gain frequency here. All right, so let's continue from that background. Just as we did that in the frequency domain, we can characterize amplifiers in the time domain as well. And so in this case, for example, the amplifier that is given, let's say you apply a step voltage. Typically, you would apply a step voltage here. And right now, the amplified version, let's suppose the phase difference between the input and the output is 0. So the output is supposed to be a amplified version of input. But the output does not rise to its final value instantaneously. It takes time. And And similarly, when you remove the input, the output does not fall back to 0 instantaneously. Again, it takes time. And sometimes you may see a response of this particular kind here that you see shown over here. And then obviously we can characterize, we can say that the amplifier has a delay, and the delay can be characterized in several terms. One of them is how much time does it take to rise time, how much time does it take to fall, and rise time could be from 10% to 90%, fall could be from 90% to 10%. So rise time and fall time are another important parameter of a amplifier here. Sometimes you don't see this simple behavior. You may see something of this kind. When you apply a step, you may see that the amplifier does not gradually go to its final value. It shows this ringing behavior here. It overshoots and then gradually settles down here. So in those cases, besides rise time and fall time, it's also important to know how much is the overshoot. This is the steady state value. So you would like to know how much is the overshoot in the amplifier here. What percentage is this one as compared to the steady state value here. So overshoot becomes an important parameter of the amplifier as well. The other thing is, how long does it take to settle down to its final value here? So settling time. So that, starting from this point onwards, so this is where it rises to its maximum, and how long is it taking to settle down to, within a few percent of its final value here. So settling time is important as well when we look at the time response here. All right, so that's as far as the time response or the frequency response is concerned. Okay, rise time, fall time, overshoot, settling time are in the time domain. Lower cutoff frequency, upper cutoff frequency, or unity gain frequency are in the frequency domain. Let's look at another non-ideality. So that was frequency. And the other one, very important, is that the amplifiers in general are nonlinear. And the reasons for it are that they are made up of elements. You see a simple amplifier here. The elements themselves are nonlinear. The transistor, whether I take a bipolar transistor or I take a MOSFET, is a nonlinear element. As an example, if you look at here, without going into the details of it, the collector current that you see here in a bipolar transistor as a function of base emitter voltage here. All of you know this is the base and the emitter here. The collector current as a function of base emitter voltage is nonlinear. It's in fact exponential in nature. Now if you look at how amplification is occurring, well, this input voltage here, what does it do? It modifies the base emitter voltage. It increases the base emitter voltage or decreases it by a certain amount if it's a sinusoidal. So the input is modifying the base emitter voltage. The modification in base emitter voltage results in modification in collector current, and that shows up as a modified or whatever output voltage here. So if the relationship between IC and VBE is nonlinear, the relationship between collector current and input voltage will also become nonlinear. The output would also have nonlinearity. So nonlinearity is inherent in all transistors. The issue is, how do we manage it? How do we keep it small? Because ideally we would like V0 to be linear with Vin. Now, so now that we know that nonlinearity is there, how do we quantify it? How do we tell this amplifier is more linear than the other? Well, there is a way of doing it, and that is using what we call as harmonic distortion. One of the consequences of nonlinearity is that if you feed in a sinusoid here at the input, you don't, let's say sinusoid of frequency F0, you don't get a sinusoid of frequency F0 at the output. You get harmonics also because of nonlinearity. If the amplifier were linear, if you feed in 1 kilohertz sinusoid, you'll only get 1 kilohertz sinusoid output. But if it's nonlinear, instead of 1 kilohertz at the output, you may get 2 kilohertz and harmonics. 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on and so forth. So one of the ways of measuring how much is the nonlinearity is by measuring the harmonic distortion. So what we do is, we feed in a sinusoid, Vin, let's say is A0 sine omega t, and at the output what you find in general is you may find some DC value that is there. Let's ignore that for a moment. B1 sine omega t. So you get corresponding to omega, you get a omega output also, which we expect and which we want, but you get harmonics also. You get sine 2 omega t, sine 3 omega t, and so on and so forth. That's the consequence of nonlinearity. So we can define a harmonic distortion. We can define second harmonic distortion, HD2. 2 refers to second, and HD, of course, is harmonic distortion, as the ratio of B2, the amplitude of the second harmonic, divided by the fundamental. The fundamental is what you want. B1 is what you want, what you're looking for. So B2 by B1 gives you, and in terms of percentage, then you multiply by 100. So you get second harmonic distortion, HD2. Or HD3, which is the amplitude of the third harmonic divided by amplitude of the first fundamental here. So that gives you HD3, third HD3. And similarly, you'll have HD4, HD5 and all that. One can sum them up. Normally, they are summed up in a RMS fashion here. So what you do is, you take B2 by B1 square plus B3 by B1 square. You sum it up all up in an RMS fashion. And that is called the total harmonic distortion. So that becomes an important characteristics of an amplifier here. So when you're saying my amplifier has a gain of 100 and you're giving its lower cutoff, upper cutoff and all that, it's also important to specify how much is the harmonic distortion, total harmonic distortion, THD. So THD is a measure of how nonlinear your amplifier is. Let me take an example here. That example would illustrate. Let's take an example where output voltage V0, an amplifier, of course, so output voltage V0 is related to Vin in this manner, K Vin, plus we've added a nonlinearity here. Ideally, we would want only the first term, But in addition to the first term, we are getting a nonlinearity. Let's say k by 10 some v in square. It's a hypothetical example. So we would like to find out how much is the harmonic distortion here. So our procedure is what? We feed in a sinusoid. So we say, let's say v in equal to a naught sine omega t. We take this, we plug it into this expression here, and output then comes out to be, we can expand it, output comes, there'll be sine omega t here, and there'll be a sine square. Sine square, of course, you convert it back into cos. And so you see that there is a fundamental component, and then there is a second harmonic. So in this case, because of the nonlinearity is small, it's only a square. It's not a very strong, exponential is a very strong nonlinearity. Square is a relatively smaller nonlinearity here. The only thing that we get is the second harmonic here. So we can calculate here, total harmonic distortion is same as HD2, which is basically the ratio of the second harmonic divided by the fundamental here, and that in terms of percentage comes out to be 5A naught here. So what you realize is that the harmonic, total harmonic distortion depends on the amplitude of the input that you apply here. And that's an important point. Distortion increases with the magnitude of input voltage in general. Now, as you increase the input voltage, obviously, the output voltage is also increasing. So another way of saying is that distortion increases with the output voltage. The higher the output voltage, the larger in general the distortion. Another way of stating is, why do you want a higher output voltage? Because you want a higher output power. So as you want more and more output power, the distortion would increase. Okay, how it increases and all that, that depends on the details of how the amplifier has been designed, whether it uses a bipolar or a MOS, whether there's a negative feedback, and all kinds of details would decide how much is the distortion. And I'm sure all of you are familiar with any system, any music system or whatever. As you increase the power, you may, beyond a certain point, you may find that it's not sounding very nice. And the reasons for that are that the distortion increases with the power level, output power level. Okay, all right. So that's coming out from this particular, and that's understandable. I mean, if something is nonlinear, if I apply a larger input voltage, the effects of nonlinearity would be larger. So we have looked at now a couple of parameters, and total harmonic distortion and its components, second and third and all that harmonics, are also important, and they need to be specified when we are talking about an amplifier here. Now, talking about output voltage here, this shows a output voltage versus input voltage graph here. Now, when I'm building an amplifier and I'm writing a linear relationship, I'm saying that if you apply a certain input voltage, you get a certain output voltage, right? If I apply a certain input, I get a certain output. But then, besides the nonlinearity, what happens is there's a limit to how large an output voltage I can get. If I keep on increasing V in, eventually, what I find is that my output saturates. There's a limit. There's a finite amount of supply voltage that you've applied here. It's not that you can keep on increasing V in and output would keep on increasing proportional to it. A stage will come when the output would saturate, whether in the positive direction or in the negative direction here. And so these are, when I write here VOH, this is the absolute maximum voltage swing that you can get here. Okay, so we call this as the maximum voltage swing, VOH. And similarly on the negative side, maximum voltage swing on the negative side here. So that's also important, right? So when you're specifying an amplifier, you would like to know how large an output voltage can I get? How much is VOH and how much is VOL? Okay, and in this context, so you can see what would happen if you're clear of VOH and VOL. If you're less than the maximum output voltage and you apply a sinusoid or whatever, you'll find that the output is also a reasonable sinusoid. But if you drive an amplifier hard, what would you start to notice? You would start to see clipping, because the output cannot go beyond this. Your sinusoid is expecting to go up to, let's say, 6 or 7 volt on the positive side, 6 or 7 volt on the negative side, but there is an absolute limit of an amplifier here. You can't go above the maximum voltage swing, so you would start to see a clipping here. The sinusoid would be clipped at the top. The sinusoid may be clipped at the bottom. So clipping is one of the consequences if you drive an amplifier very hard. And clipping represents what? A very severe form of distortion. Because of this clipping, if I analyze this particular sinusoid with a clipped output, what I would find is that there are a lot of harmonics that are there. There'll be a second harmonic, third harmonic, fourth harmonic. So what is really happening is what we are saying in another way is if you drive your amplifier starting from lower voltage, if you drive it, what would happen is the amplifier is increasingly getting nonlinear. Harmonic distortion is increasing. But at a certain stage, what happens is you reach this limit. And that's the absolute limit, maximum voltage swing. And at that point, you get severe distortion in the output. You start getting clipping. Okay, you get severe distortion and your harmonic distortion would increase drastically here at this particular point. Okay, so it's also important besides, harmonic distortion. If somebody tells you total harmonic distortion in this amplifier is 1%, what does it mean 1%? It means, let's say second harmonic distortion is 1% means the second harmonic is 1% of the first harmonic, right, of the fundamental. But besides that, you also have to know is what is the maximum voltage swing? Because that's not the complete story, right? Harmonic distortion, as I've been saying, increases, but when you reach this particular limit, it's not just 1% or 2%, it may become very large because you get severe clipping here. So maximum voltage swing is an important parameter of an amplifier as well. You would like to know that. And in this context, what we would like is, I've shown an amplifier here which is driven by a positive power supply which is VDD and a negative power supply VSS. For example, your 741 op amp, we typically apply plus 12 volt here and minus 12 volt here. Now at the output that you see here, typically we would like it to go as far as on the positive side as VDD. In a typical amplifier, if it's a good amplifier, the output voltage, you could drive it almost towards VDD here. And similarly, on the negative side, you could drive it almost to VSS here. In an amplifier where you can do that, where positive voltage swing is VDD and negative voltage swing is VSS, we call such an amplifier as an amplifier which gives us rail-to-rail output voltage swing. Rail-to-rail in the sense, this is the positive rail and this is like the negative rail here. Okay, and an amplifier which gives you right up to VDD here and right up to VSS here is considered as a good amplifier which provides you with rail-to-rail output voltage swing. So when you look at the data sheets of amplifiers made by different manufacturers, you'll find, one of the things that they may be claiming or advertising is that my amplifier gives you rail-to-rail voltage swing. Now, what does rail-to-rail mean? It means that it can go right up to positive power supply and right up to negative power supply. That's what rail-to-rail output voltage swing is. Okay, so that's coming back to this particular expression here. So we have seen amplifiers characteristics with respect to frequency. We just saw with respect to Vin, the input voltage, the harmonic distortion, and all that. The amplifier's characteristic depends on also what it is connected to. Let's look at this example here. Effect of load resistance here. All right, so let's this is our amplifier, and what we have done in this amplifier, we have connected a load resistance RL, and we've also connected a source resistance RS and VS here. This is the signal that we want to be amplified, and overall amplification is V0 divided by Vs. That's the overall amplification, V0 by Vs here. Sometimes we define V0 by Vs here. If let's say RS is negligible, or sometimes you may also define V0 by Vin, depending on your interest. Okay, obviously the signal of interest is Vs, so V0 by Vs is there. If I look at this amplifier, look at the gain of this amplifier, and look at it as a function of RL. All right, I look at my amplifier, the overall gain V0 by Vs or V0 by Vin, whatever it is. I look at it as a function of RL. Now, typically, what I would like is my amplifier gain should be independent of RL. When I'm making an amplifier and I claim that its voltage gain is 100. Now, some user may connect 1K, drive using my amplifier, drive a 1K load. and he should, he's expecting that he would get a gain of 100. Another user connects 10 kilo ohm, well, he should also get a gain of 100. So typically or ideally what I would like is my gain should not depend on RL. Should be independent of RL. No matter what RL the user connects, he or she gets the same value of the voltage gain. But in practice, what do I see? If I start from a very large value of RL, the gain is flat. But then as I keep on reducing RL, a stage comes when the gain begins to fall. The gain begins to fall, and the place where the gain falls to half of its maximum value, that particular value of RL is what we call as the output resistance of the amplifier. So what is really happening is that the amplifier that you see here will show you this the equivalent circuit of the amplifier in a minute. So the amplifier has a parameter called the output voltage here. Because of this output resistance, the gain of the amplifier falls as I connect smaller and smaller values of R. So when I look at my amplifier, so what is happening is when I look at my amplifier, right? When I look at my amplifier from the output side, okay, from the output side, what does it look like? Well, I can construct sort of a Thevenin's equivalent. My amplifier from the output side looks like this. A voltage controlled voltage source. Voltage control, look at this symbol here. So it's a voltage source controlled by what? Controlled by the input here. And with an amount AV0 times Vin. AV0 refers to voltage gain in the open circuit condition. And you can see why this would be the gain in the open circuit condition here. So my amplifier looks like AV0 into Vn and in series with an output resistance R0. That's my amplifier when I look at it from the output side. And then we have connected a load to it. Right? So now it's obvious that if I look at my output voltage V0 is AV0 times Vn here. There's a voltage divider RL by R0 plus RL. So it clearly shows that if RL is very large, for example, if RL is infinity, it's open circuit, obviously V0 is simply equal to AV0 times Vn. And that's why we call it the open circuit voltage gain. As RL reduces, initially nothing happens here because RL may be still very much larger than R0. Nothing really happens here. We get a constant value of V0. But if RL starts becoming comparable to R0, then we see that the output voltage starts falling. Okay? So the amplifier then on the output side, when I look at it from the output side, is modeled or is described by a resistance R0. Every amplifier will have a certain amount of R0. And because of this R0 output resistance here, gain begins to fall at lower values of load resistance here. So for an amplifier then, what kind of an R0 should I have? Ideal amplifier has R0 equal to 0. Right? Ideal amplifier will have R0 equal to 0 here. Which means when you put R0 equal to 0, no matter what RL I connect, my gain is independent of RL. That's an ideal amplifier. All practical amplifiers will have a certain amount of R0. And from a voltage amplifier, we're looking for R0 as small as possible. If R0 is small, then my amplifier, the user of my amplifier can connect any value of RL and get the same value of voltage gain. Okay, so another important parameter of an amplifier then is what we call as the output resistance of the amplifier here. And you should remember this equivalent circuit. My amplifier, when I look at it from the output side, is a voltage controlled voltage source with a series resistance R0 connected to it. So that's the simple description of an amplifier when I look at it from the output side. Obviously, what you're seeing here is there is an approximation here. We just talked about that my amplifier is nonlinear in nature, right? And I'm building a Thevenin's equivalent of this one. You know that Thevenin's equivalent and all that I built for linear circuits here. So when I'm building this particular picture here, what I'm saying is, yes, harmonic distortion is there, but is relatively small and to the first order approximation. When I'm talking about R0, I can neglect it here. Okay, so I'm modeling it as a linear amplifier here with a AV0 open circuit voltage gain and a output resistance R0. Now, Similar to R0, there is a input resistance as well. Now, this is an experiment that you can do. You can take an amplifier, any amplifier. You can connect a load, but you might leave it open also. Say V0 is there, and you attach a source Vs and Rs, and you calculate the voltage gain. Voltage gain overall is V0 by Vs. And you plot voltage gain for various values of Rs. What you would find is if Rs is low, gain is flat. But then if you keep on increasing Rs, a stage comes when gain begins to fall. And the value of the Rs for which the gain falls to half is what we call as the input resistance of the amplifier. Okay. So again, this kind of a behavior we can explain by building a model for an amplifier when you look at it from the input side here. A very simple description of an amplifier when you look at it from the input side is nothing but a resistor. Amplifier, when you look at it from the input side, it appears to your load, it appears to your source like a resistor here, Rn. And we call this the input resistance of the amplifier. And we've already seen that when you look at it from the output side, it looks like a voltage controlled voltage source in series with a resistor R0. So the overall amplifier, this amplifier that you see here, can be described by a Rn here, input resistance here, an open circuit voltage gain, a voltage dependent source here, and a resistor R0. So that's my amplifier that you see here. Okay. And then of course you connect a source and you connect a load, and a lot of amplifiers characteristics can be explained by this very simple model here. And so we can clearly see then that if Rn is small, then because there's a voltage division here, and what really gets amplified, as you can see here, is not Vs. What really gets amplified is Vin, the voltage that appears as at the input of the amplifier here. So if Rn is small, and because of this voltage division, then a smaller fraction of Vs appears at Vin, and obviously then the overall gain would be smaller here. So what you're looking for is an amplifier with a very large value of Rn. If Rn is very large, then the entire Vs that you have will appear here, and then result in the output voltage here. So for a voltage amplifier, we are looking for a input resistance which is as high as possible, ideally infinite. Okay, but all practical amplifiers would in general have a certain amount of resistance that is there. Okay. Now, if you look at this picture, you can clearly see, this is the amplifier that we are building, right? This is the amplifier that we have built with an Rn, AV0 Vin, and R0 here. Now, can you see a limitation of this amplifier? Right in the beginning of our discussion, we said an amplifier has a frequency response, right? Its characteristics vary with frequency. You don't see any frequency response here, right? There are only resistors here. In this case, V0 versus Vs is totally independent of frequency. Where does the frequency response come into picture? So this picture that we are building is a picture which is valid in the mid-frequency range. Remember we said there's a mid-frequency range, then there's a lower cutoff frequency, there's an upper cutoff frequency. In the mid-frequency range, the gain is independent of frequency. So in that region, in the mid-frequency region, you can build an equivalent circuit of an amplifier in this particular manner. If you go towards very high frequencies or very low frequencies, this picture is not correct. In addition to resistors that you see here, there are capacitors also inside the amplifier. Capacitors that are there, and those pictures, those models would be valid at higher cutoff frequencies and lower cutoff frequencies and all. In the mid-frequency range, you can think of your amplifier as described by these elements only. Frequency independent elements, gain is flat or independent with respect to frequency. Okay? So we have learnt of two more parameters, which is the input resistance of the amplifier and the output resistance of the amplifier. Another important parameter of an amplifier is noise. So in an amplifier, we said that, we just learned that you cannot apply higher and higher values of Vs and expect that the output voltage would follow Vs. Because eventually what happens, we said the output would saturate to some positive value or negative value. Similarly, You can't apply smaller and smaller values of Vs and expect that the amplifier would continue to amplify. Now I'm going on the other side. First I was saying there's a limit to how large an input voltage you can apply or how large an output voltage you can get. Similarly, there's a limit to how small an input voltage I can apply and still my amplifier would amplify it properly. And this I want to illustrate through this example here. All of you are familiar with an op-amp. You've used an op-amp before. And so in this particular picture, it shows a amplifier, an op-amp amplifier. You can see here the gain of the amplifier is the ratio of these two resistors here, gain of 100 here. And similarly, this amplifier also has a gain of 100. The capacitor is simply to couple the input of this one to the output of this particular amplifier to the input of this one while blocking the DC. Okay, so capacitor is just for connecting the two. So don't worry too much about it. So we have an amplifier with an overall gain of 100 multiplied by 100, 10 to the power 4. Right? But notice something. I've not applied any input to the amplifier. Normally, to the amplifier, I would connect an input here. Okay, we would connect an input here, and then we would get an output voltage here. So I've not applied anything to the amplifier. If my amplifier is ideal, when I apply 0 input voltage, I should get 0 output voltage. I've not applied anything, so I shouldn't get anything out. Right? So I'll show you, these are experimental measurements of an actual circuit put together in the lab. This is what you get. Look at the output. Here, right here, at this particular point. Nothing was applied here, but this is what you get at the output here. Now, when something is random like this, you don't specify a random voltage in terms of, only in terms of what is the peak value and all that. A better measure is what is the RMS value, root mean square value. So if you can read here, the RMS value at this particular one, RMS of the output is 738 millivolts of RMS voltage is there. So let's take it as a round number. 750 millivolt is the RMS voltage here. 750 millivolt. Random signal that you see. Where has it come from? I've not applied anything at the input. Where has it come from? 750 millivolts of RMS voltage here. That's significant, right? 750 millivolts is a significant number here. Where has it come from? Well, as I said, all the elements that you take, every resistor that you take here is a source of noise. Every transistor is a source of noise. It generates noise. The movement of electrons in a resistor is random in nature. The movement of electrons and holes inside a transistor is random in nature. There is randomness inherent in all the devices that we handle. Resistors, transistors, diodes, there's an inherent randomness in them, the way the carriers move. And they're all sources of noise. So my op-amp here that you see here, this is an amplifier. The op-amp is generating noise. The resistors are generating noise. Similarly, this op-amp is generating this resistor, this op-amp. They all generate noise. All the noise is getting combined, and we are looking at the total amount of noise at the output. This is true of all amplifiers. You don't feed in anything at the input, at the output, you will always find certain amount of noise that is present. So if I look at this picture here, let me ask you with this, and the output voltage is 750, let's take it, 750 millivolt RMS. How small an input voltage can I amplify in a reliable manner? How small an input voltage can I amplify here? Now, if I've built an amplifier, obviously I'm not going to connect it to ground. I would connect a source here. I would like to amplify it. How small an input voltage can I amplify in a reliable manner? Is there a limit to how small? Can I amplify a 1 microvolt signal? And still, let's say I have a 1 microvolt here, 1 microvolt sinusoid. Will I get a nice 1 microvolt sinusoid at the output? Oh, sorry, an amplified version of 1 microvolt sinusoid at the output? No, right? The sinusoid would be actually submerged in the noise. It's not a useful signal. So how small can I apply here an input voltage and still get let's talk about a sinusoid. how small a sinusoid can I apply here and still get a relatively clean sinusoid. So I can really see noise would be there, but compared to the signal, the noise is small. So how small can I apply? How small do you think I can apply? Well, this is the output noise, right? Output noise is what? 750 millivolt. When you take this 750 millivolt here, this noise, and you transform it to the input, what kind of an input does it correspond to? It's as if you can think of the following. 750 millivolt of output noise that is there here. If I transform that particular noise towards the input side, it's as if 750 divided by 10 to the power 4, which means what? 750 divided by 10 power 4 is how much? 0.075, right? So it's as if my amplifier is, you can think of in the following way. It's as if my amplifier is clean. There's no noise in my amplifier. But there is a noise voltage here in series with my amplifier. Right? Either, I can take all the effects of the noise that you see here, noise generated here, and all that, and I can take all of that and transform it back to the input, and I say as if there is a noise voltage in series with it. Some amount of noise voltage in series with it. What does that noise voltage do? Now this amplifiers and all that are all clean, noiseless. So if I have 0.075 or whatever millivolt of noise that is there, that will go through the gain and will appear over here. So let's say, for a hypothetical case here, let's say my input referred noise voltage. Does everybody understand what I mean by input referred noise voltage? It means whatever is the noise voltage that I'm getting here, I divide it by the gain of this amplifier. And I put that noise voltage in series with the amplifier. And I call this as the input referred noise voltage. Let's say the input referred noise voltage is 0.1 millivolt. How much signal can I amplify then? Obviously, if I apply a signal also equal to 0.1 millivolt, the output is not going to be clean, right? So at least if my input referred noise voltage is 0.1 millivolt, maybe I should apply a signal which is at least 10 times stronger than the noise voltage here. So I can amplify without too much impact of noise, maybe 1 millivolt. So the point is that every amplifier has what we call as noise in it. We can describe the noise by various means. One of the ways of describing the noise is how much is the input referred noise voltage. So input referred noise voltage becomes an important parameter of an amplifier. If the input referred noise voltage of an amplifier is very low, then it's a good amplifier. We would call it a low noise amplifier. If the input referred noise voltage is large, well then I'm in trouble. Then small signals I cannot amplify. Okay, so what you are seeing is the noise property of an amplifier is also very important. Now, most of the time, if you're not pushing the limits, the input referred noise voltage is so low that you don't bother about it. Your signals are much larger, and you don't encounter noise. But if you're pushing the limits, if your signals are very weak, you will encounter noise as a fundamental limitation in your amplifier. Okay, so that's something that you will have to wrestle with as you go towards lower input voltage, lower input power. Noise becomes extremely important. As I said, there are many ways of quantifying noise. One of the ways is input referred noise voltage. Another way that people talk about is the following. They talk of noise in terms of noise factor and noise figure. Now, what is noise factor? Noise factor is total output noise power divided by output noise due to input noise only. Now, what do we mean by that? Well, when you see noise at the output, the noise at the output can come from where? Can come from the amplifier itself, noise which is generated in the amplifier, or it can come from any input noise. No signal is a clean signal. In the lab, fine, you may have a very nice sinusoid, but in real life, no signal is a clean signal. It always comes with some amount of noise in it. Okay? So there's always an input noise. In a real system, there's always an input noise. So when you look at noise at the output, the noise at the output is due to noise at the input which is getting amplified by the amplifier, plus noise which is generated by the amplifier itself. So what we are talking about, noise factor, is total output noise power divided by output noise due to input noise only. So what should be the ideal value here? An ideal amplifier would do what? An ideal amplifier would not add noise to it, right? So ideal value of noise factor is 1. Ideal value of noise factor is 1. At the output, you only get noise which is already present in the input, and that just gets amplified. But if the amplifier is adding more noise, then the noise factor will become larger than 1. Okay, so noise factor is another way of measuring the importance of or how noisy your amplifier is. And the noise figure that you may read, another way of specifying noise figure is nothing but noise factor specified in terms of decibels. 10 log of this gives you a noise figure here. So as an example, I can have a noise factor of 1.26. 1.26, and noise figure would then be 1 dB. That would be a pretty nice amplifier here. That the output noise is only 26% higher, and that translates into noise figure of 1 dB. Right? So another important specification of an amplifier then is related to noise. And noise, as I said, can be specified in many ways. One of them is noise factor, noise figure. Sometimes we specify it in terms of how much is the input referred noise. So there are multiple ways in which noise is characterized. These are some of the common ones in which we do it. So it's an important part of an amplifier, but in this particular course, this is all that you'll hear about the noise here. We are not going to, there are many other things to handle in this course, and so noise is not something that we'll be able to address. And so that's the last that you'll hear about noise. Okay, so noise figure and noise factor are important. We know that when you go to very low values, you'll probably hear more of them as you go further in the curriculum. In the graduate courses, you'll have more discussion related to noise aspects. All right. Before I conclude with a discussion related to amplifier parameters, there's one more important characteristics. In fact, there are many important characteristics of amplifier, but another which is important when I talk in terms of output. So this one shows you a 741 op-amp, which is and we are building a inverting amplifier with 1K here and 10K here. The 741 op-amp, when I look at it from the output side, has a very, very low output resistance here. Very, very low. R0 is less than 1 ohm. Okay? Less than 1 ohm. Now, in light of what we have just discussed about amplifiers and output resistance, if I connect a resistance here of whether 1K or 10K, does it really matter? Output resistances are not. For what value of RL do you think my output will begin to get affected? What did we say about R0? When RL starts to become comparable with R0, then my output becomes sensitive to RL. What value of RL I connect? If RL is much larger than R0, it doesn't really matter. Whether you connect 1K, 10K, 100 ohms, if R0 is less than 1 ohm, whether I connect 100 ohms or 200 ohms or 300 ohms, it really should not matter. That's what output resistance is telling you. That it doesn't matter what value of RL you connect, as long as RL is much larger than R0, it doesn't matter, output voltage would remain the same. But that's not the entire story. So we expect in this case that the gain of the amplifier is 10, the ratio of these two resistors. So if I apply minus 1 volt, I should get 10 volt at the output. 10 volts at the output. Let's say the supply voltages are plus minus 12. So I'm away from the supply voltages and the op-amp is not such. So let me do this experiment here. You can do it in the lab. You can make this amplifier here. And what you can do is you can start to reduce RL. Take large value of R0, RL, start with large value of RL and start to reduce RL. When would you expect to see output voltage dropping? Because we're keeping input constant and we expect output voltage to be 10 volt. And if I keep on reducing RL, I would expect changes to occur when RL starts to becoming comparable with R0. And let's say when RL becomes equal to about 10 R0 or something like that. Because we know that when RL equal to R0, the output has already fallen by half. Okay? So when RL is becoming comparable to R0, we may expect that this should fall. It should fall here, right? At this value of 10 R0. For the sake of argument, let's say R0 is 0.1 ohm. If R0 is 0.1 ohm, I expect it to fall around 10 times R0, I expect it to fall around 1 ohm. If I connect RL of 1 ohm, then only I should expect things to happen. If I'm clear of that 1 ohm, I expect output to be flat, independent of RL. In real life, what happens? The red graph. In real life, what is happening is, as I decrease my RL, it is flat, fine, but it begins to drop at 400 ohms. At 400 ohms, it begins to drop. Now, 400 ohms of RL is much, much larger than R0 of 0.1 ohm. Why is it dropping? The whole idea of R0 was that if RL is much larger than R0, output voltage should not be affected by RL. Well, RL is much larger than R0 here. But it is dropping. It begins to drop. And to clarify this, what we are saying, what we want to illustrate is that every amplifier has a maximum current drive capability. Every amplifier. Just like we said, every amplifier, the output will not keep on following the input. There's a maximum output voltage swing that you can get. Similarly, that was in terms of voltage. This is in terms of current. Every amplifier has a current limit. The amplifier cannot supply more current than that particular maximum value. It has a current limit. Your op amp, for example, 741 op amp, has a maximum current capability of 25 milliamperes. So besides the output resistance and all that we studied, this is another parameter which is important. You should not violate the current limit of 25 milliamperes here. So now you see what happens here. When -1, I'm expecting 10 volt here. And when I connect 400 ohms, the current required by my load is right there at about 25 milliamperes. If I make my load smaller, your load is asking for current larger than 25 milliamperes. Your load is demanding, for 10 volt, the load is demanding current which is larger than 25 milliamperes. Your op amp cannot supply. It can't supply that much. So what would happen? The load is demanding more current. The op amp cannot supply here. So what happens? The output voltage drops. It's no longer 10. Because the maximum current that can flow into the load is 25. That's what the op amp can supply. So the output voltage will fall. So the reason why the output voltage is falling is not because of output resistance considerations, but because my load is demanding a current which my amplifier cannot supply. Amplifier cannot supply, and therefore the output is actually dropping. So every amplifier has a maximum current drive capability. For 741 op amp, it is 25 milliamperes. For some other amplifier, it may just be 1 milliampere. Or for some, it may be 100 milliamperes here. Okay? So that's another thing to be clear about. That there is I can't just connect any value of RL, and that RL is much larger than R0, so I should expect output to behave properly. The answer is, well, it would behave properly as long as you don't violate the current limit. Then you're fine. Okay? So that's another thing. So let me summarize our discussion. What we have said is that a practical amplifier has a number of limitations, a number of non-idealities. We saw that voltage gain, we should actually talk about voltage gain, open circuit voltage gain in the mid-frequency range. So when we say an amplifier has a voltage gain of 100, we mean mid-frequency gain, and that also in the open circuit condition, AV0. The amplifiers has a dependence on F, and we said that is specified by bandwidth. I've not written time. on the time side specified by rise time, fall time, and all the other things. Its dependence on input voltage means the amplifier is nonlinear. And so we specify that in terms of harmonic distortion. The dependence of amplifier on RL we specify in terms of output voltage. Output resistance. And in addition to that, I should add an output current drive capability. The dependence on RS we specify in terms of RN, the input resistance. The dependence on noise we specify in terms of noise figure, noise factor, input referred noise here. Besides that, there are many other parameters that are there here. There is efficiency of an amplifier, there's power supply rejection ratio, common mode rejection ratio. There are many other parameters of an amplifier. As we go along the course, we may refer to some of these later on. So for now, these are the factors that you should be aware of, and these are the factors with which we'll work for the remainder of the course.